Hello students and welcome. Today we're going to tackle a really important topic from our atoms chapter, and that's atomic spectra. Now look, I know this one can feel a bit tricky, a bit confusing sometimes, but I promise you by the end of this session it's going to feel super simple and more importantly, completely safe for your exams. Chalo, let's begin.
So, let me start with a simple question for you. We all seen those bright, glowing neon signs on shops, right? But have you ever stopped to wonder, why does neon always glow with that specific bright red-orange color? Why not blue or green? Well, the answer to this little mystery is hidden deep inside the atom, and that's exactly what we're going to uncover today.
Alright, so you know that when we pass sunlight or even light from a simple bulb through a prism, what do we get? We get a beautiful, complete rainbow, a continuous band of colors. This is what we call a continuous spectrum. But, and this is the most important part, if we take a gas, say the neon from our sign, heat it up until it glows, and pass that light through a prism, we don't see a rainbow at all. No, instead, what we see are just a few sharp, separate, bright lines of color. This is called a line spectrum.
So, what's happening here? Well, the best way to understand this is to think of an atom like a musical instrument. Let's say a piano. Now, a piano can only play the specific notes that have keys, right? You can't just play a sound that's somewhere in between two keys. An atom is exactly the same. It can only play or emit certain fixed colors of light. It simply cannot produce the colors in between. Every element is like a different instrument, tuned to play its own special set of notes.
And that brings us to the proper definition. This is the one you need to write word for word in your exam to get full marks, okay? An atomic spectrum is the set of discrete wavelengths of light emitted or absorbed by atoms of a particular element. Let's just quickly break that down. Discrete just means separate and distinct. So really, it's nothing but the unique pattern of light colors that a particular element gives off. It's like a fingerprint or maybe a barcode, but made of light. And just like a fingerprint, no two elements have the same one. It's bilkul unique.
Okay, so we've established that every element has its own light fingerprint. But how is this fingerprint actually made? What is going on inside the atom that produces these very specific lines of color? To figure that out, we are going to look at the simplest atom of all, our good friend, hydrogen. It's the perfect example to decode this whole process. You know, the whole thing is actually a very simple four-step process. First, energy in. The atom gets a kick of energy, maybe from being heated up or from electricity. Step 2, jump up. This extra energy makes an electron jump up to a higher energy level, which is not very stable. It can't stay there for long. So what happens next? Step 3, fall back. Almost instantly, the electron falls back down to a lower, more stable energy level. And this is the most crucial step. Step 4, light out. As the electron falls, that extra energy it had has to be released, and it's released in the form of a tiny packet of light we call a photon. And that photon, that is the line of light we see.
So, the next obvious question is, what color will this light be? Well, that's also very simple. It all depends on the size of the fall. If an electron makes a very big jump down from a high level to a much lower one, it releases a high-energy photon. We see that as blue or violet light. But if it makes just a small jump down between two levels that are close together, it releases a low-energy photon, which we see as red or orange light. So, the energy gap, it directly decides the color. Simple, isn't it?
Now for hydrogen, all these possible jumps have been very neatly organized into groups or families, which we call spectral series. And it's all based on which energy level, or N, the electron lands on. So if you look at the table, any jump that ends on the first level, N equals 1, is part of the Lyman series. These are all big, high-energy jumps, so the light they produce is in the ultraviolet. We can't see it with our eyes. Now, any jump that ends on the second level, N equals 2, is part of the Balmer series, and this one is very important for us, because these jumps produce visible light, the colors we can actually see. And then, jumps that end on level 3 are called the Paschen series, and they fall in the infrared region. Let's zoom in on one very specific, very famous line in the hydrogen spectrum. It's a beautiful, bright red line, and it has a very precise wavelength, 656 nanometers. Now, this is not just some random number. It's a fundamental signature of hydrogen. And the amazing part is, the theory we've just discussed can predict this exact number. Let's see how. So this famous red line comes from one particular jump, an electron falling from the third energy level down to the second one, from N equals 3 to N equals 2.
Now, how do we know this for sure? Well, we have a very powerful tool called the Rydberg formula. Don't worry about memorizing the whole equation right now, just focus on what it does. You can think of it like a special calculator for these jumps. You just tell it the starting level, which is 3, and the ending level, which is 2. And it calculates the exact wavelength of the light that should be emitted. And when we plug in 3 and 2, guess what we get? Almost exactly 656 nanometers. This is the magic moment, you see. It proves our theory isn't just a nice story. It perfectly predicts what we see in the real world.
Okay, the core concepts are clear, I think. So now let's change gears a bit and talk about your exam. To make sure you get full marks, we need to be aware of some common mistakes, some silent killers that can cost you marks. Let's look at them now so you can avoid them completely.
Okay, here's the first trap. A lot of students think that anything that's hot will glow with all the colors of the rainbow. This is a very common mistake, and it's absolutely wrong. Here is the correct fact you must remember. Only a hot, solid, like the filament in an old light bulb, gives a continuous rainbow. A hot gas, on the other hand, where the atoms are all separate and isolated, will always give a line spectrum. So for your exam, just remember this simple rule. Gas gives lines. That's it. A hot gas gives you a line spectrum. Simple enough.
And here's the second big trap. When students see that a hydrogen lamp is giving off multiple colors, red, blue, violet, they sometimes think that there must be some impurities in the gas, or maybe different kinds of hydrogen atoms. Again, this is not correct. The truth is, all of those different colors are coming from identical hydrogen atoms. The only thing that's different is the type of jump the electron is making. You see, a jump from level 3 to 2 gives that red color. A jump from 4 to 2 gives a blue-green color. It's the same atom, just different jumps, creating different colors. That's all there is to it.
So we've looked at all the details, the jumps, the lines, the colors, but now let's just zoom out for a moment and look at the big picture. Why is this topic so important? Why does this whole idea of a light fingerprint change everything we know about physics and the universe? Well, there are 3 huge reasons. First, the very existence of these sharp lines is the ultimate proof that energy inside an atom isn't continuous. It comes in fixed packets or steps. In other words, energy is quantized. Second, it was this exact discovery of spectral lines that was the clue that led Niels Bohr to create his revolutionary model of the atom. And third, this is the foundation of a whole science called spectroscopy. By simply reading the light fingerprint coming from a distant star, we can tell exactly what elements it's made of, without ever having to go there.
So, before we finish, let's quickly summarize the 4 key points that you must have at your fingertips for your exam. Number 1, every element has its own unique line spectrum, its special atomic fingerprint. Number 2, these lines are created when electrons jump between specific allowed energy levels. Number 3, the color or wavelength of the light depends on the size of that energy jump. And number 4, the hydrogen spectrum is neatly organized into series, like the Lyman, Balmer, and Paschen series.
And I'll just leave you with this one final thought to think about. If every single atom in the entire universe, from the atoms in the screen you're watching this on to the atoms in the most distant, faraway star, if every one of them has its own unique fingerprint written in light, just imagine the incredible secrets of the cosmos we can uncover simply by learning how to read.